We're going to go over some of that stuff from the work that I asked you to do, like sort of on your own, just to make sure you're feeling okay with it. If you're not feeling awesome about the algebra part, don't blame yourself. They have tossed a lot of the algebra out of the math curriculum. So I do have what I like to call remedial algebra, which is how they should have taught it to you like in the past. And I'd be happy to post one of my grade 9 lessons from last year where I went over it in gory detail, or my grade 11 lesson from early. I do it actually with my regular 11s. So I will post those if you're interested in like getting better with algebra and that's an issue for you, then you can watch those, you can ask for those. If you have no problem with algebra, then just ignore me, okay? Yes? Would you like it to happen for this? Okay. I hadn't thought of it yet. Uh-huh. No, you can just go straight to here if you want to. No. This is not given to you, so if you want to know it, you just basically have to remember. Okay. But for some reason, for me, this one's easier to remember because that one just so I have trouble remembering the people. First things first, when you're doing questions like this, these can actually be a little bit of a gift because once you know how to do them, they're pretty straightforward. This is on page 30. Okay, these are the questions on page 30. And one of the things that you should be aware of is that you will get on the AP exam a data sheet as well as your periodic table. So the purple sheet that you got, make sure you've pulled that out for use today. And we're going to make one correction because there's a little issue on here and I'm not quite sure how it came to be, but it is the very front of the book, but it's also your purple sheet. Okay? So if you have the purple sheet, that's great. If not, it is 9.0A, page 1. So you have it 2 places. So what they give you is they give you that energy is equal to H times nu. Okay? Now, why they can't be reasonable, because I think in physics they call frequency F, which makes more sense to me. However, for whatever reason, in chemistry, we use the Greek letter nu, which looks like a V. So it's really quite irritating. Yes? But the good thing is they do define it for you. So over here, they let you know that the little sort of slanty V stands for frequency. Okay? Over on the right-hand side, they also let you know that the lambda stands for wavelength. Practice writing a lambda so it looks like a lambda, not like a K or like anything else weird. Okay? Some people have trouble with it. So just, if you're not sure about your the quality of your lambda, call me over and I'll take a look at it. Energy is pretty obvious. The one formula they don't give you is my favorite version, which is E equals hc over lambda, which is the one I like. And I don't know why I can remember that one when I have trouble remembering these two. I think it's just because they're both just multiplications and they're both just nu, and then I forget, I'm like, which one is h nu and which one is lambda nu, but here would be a good way, if I had to remember it, which you don't. If you go on the C, you will encounter waves. Oh, look at that. If you go on the C, you will encounter waves. No? Yeah? Like on the C, SEA, you'll encounter waves, and then it ends in a nu. And then E equals H, because we're Canadian, eh? Ah. This is how, I have a very good memory normally. This is how my brain works. Like it's always trying to grab and make up things that make life easy for me to remember things. So if you can do those for yourself, that's great. If not, I'm happy to share my bizarre sort of thinking with you. Yes? C is the speed of light. Yes, and in fact, that is also over here, okay? C is the speed of light. H is Planck's constant. And the correction that we need to make, that is supposed to be mole to the -1. So that's what they're going to give you. So, okay, this whole -1 business, I know I've tried to introduce it to you a little bit, okay? But you see that it does show up all over the place. No, this is given to you. Yes? But you should understand that if we write joule seconds, what does that mean? Joules times seconds. If I write joules second to the -1, what would that mean? That would be joules per second, okay? So if I write meters seconds to the -1, what does that mean? Meters per second. So you can see your speed of light is given to you in meters seconds to the -1, and you just need to understand that that means meters per second. And it's not really, it actually makes writing your units in your work tidier because you don't have like a numerator and a denominator up in your numerator, right? So if you've got E equals hc over lambda, which is my favorite version of the formula that they don't give you, then if you write your H, which is in joule seconds, right? That's your H value is in joule seconds. And then you multiply it by the speed of light, which is meters per second. And then you divide it by your wavelength, which would have to be in meters. It can't be in nanometers because then your units wouldn't cancel because you've got meters and you need to have meters. Okay, so that's the one thing, well, it's one of many things you have to be careful of. When you're doing these things, you need to make sure that what your units are consistent. If one of your units is in kilojoules, your other unit needs to be in kilojoules. If one of your units is in joules, your other unit needs to be in joules. Anytime you use a formula, your units need to be consistent. So if you've got meters in your speed of light, your wavelength must also be in meters, okay? So now if I look at this, now I can look and I can say I have meters on the top and I have meters on the bottom, so those will cancel out. And I have seconds that cancel with seconds to the -1. It's a bit of a preference thing. It's one of these things that's uncomfortable when you first start working with it. It becomes more comfortable as you become more familiar. Do you know what I mean? It's like, I don't know. How easy were chemical formulas when you first started them back in grade 9? Right? They weren't like, and now if I'm like, oh, please write me the formula for calcium carbonate, you can be like, oh, yes? So again, it's one of those things, if you don't love it, you don't have to write it that way, but you do need to be familiar enough with it to recognize what it means. Alrighty? If you, what? Are we good? Oh, okay. The electron charge you don't need for right now. Okay, that's going to be for something else later on. Yes. Yes. Oh, look at that. It's 6.022 times 10 to the 23 per mole. So what that means is that there are 6.022, and that's the number that you will use on the AP exam. You will not use 6.02. I'm sorry, I did not have it within me to go and change all the resources that are in common with my regular Chem 11 course and all the answer keys to have those 466. Okay, I just did not have it in me to do it. If anyone wants to go through all my resources and change it for me, I could make that like your volunteer work for the year, and you could do it all for me and whatever, but you would need to let me know. Yes. Yes. Okay, so that's times 10 to the 23. And we have moles to the -1, which means per mole, which at this point, you know, we have 6.022 times 10 to the 23. Whatever you want, it could be photons, it could be particles, it could be elephants, it could be whatever. Cats. I don't know what you would do with that many cats, but you know, it could be moles, like the little burrowing. You could have a mole of moles. Okay, so that's why it says mole to the -1. Somebody this morning was asking me about it, and I was like, oh, why is that -1 there? That shouldn't be there, but it should be there. And I was just, my brain had not woken up to that fact yet. So all of this will be there for you. If we go back then to, It's like whatever you want it to be, yeah. Electrons, photons, yeah, armons, yeah. Okay, and then 1.1G. There we go. A baker's mole? Is a baker's mole 7.02 times 10 to the 23? We're having a conversation over here. Oh, such good questions. I love it. Okay. So we are going to take our formula and we're going to take a look at our very first question here. And I'm going to show you how I do the algebra for this. If you don't need the algebra, you can go ahead and just chillax for a minute. Yes. Uh-huh. Yes. I know. You go, oh, I'm doing a question about frequency. Therefore, I will use the V. It's going to be clear from the question what kind of a thing you're doing. No, and quite frankly, in chemistry, you're not going to be dealing with velocity. Okay, there used to be kinetic energy is 1/2 mv squared, but we don't do that anymore. So, You don't have to worry about that. Velocity is no longer in here, okay? So we would like the frequency. We know the wavelength. We want to find the frequency. And when I draw frequency, I draw it like that, so it looks really obvious. It's like, whoa, that little, it's like the V is running. Whoa. Or, okay. So you need to ask yourself, you have to ask yourself, is there a formula that relates lambda and nu? Yes, there is. And that is C equals lambda times nu. Now to do the algebra for this, I would truly suggest solve the equation first and plug in the numbers afterwards. It's just usually easier and tidier, okay? So you want to get nu all by itself. So you want to get the variable you want to isolate. You want to get nu, 1 on the top, and 2 by itself. So this is how you solve any algebra sort of equation where you've just got times and divide by on two sides. It's already on the top. There's nothing, it's not in a denominator, so it's on the top. Now you want it by itself. There's several ways to get it by itself. Some people like to do the thing where they're like, okay, I'm going to get rid of it over here by doing a division, which means that on my other side, what am I doing? I'm sorry, wrong one. I'm getting it by itself, so I have to get rid of the lambda. So I'm going to put lambda down here so that those will cancel out. And I'm going to put lambda down here because what I do to one side, I must do to the other side. Okay? That's one way of solving it. I personally find that distressing and untidy, but if you like it, go for it. It doesn't bother me what you do. What I like to do when I have a variable that I want to move, variables can move diagonally across the equal sign. Variables can move diagonally across the equal sign. So if you have a variable on the right-hand side, and you don't want it on the right-hand side because it is cluttering up your nu, you can move it to the left-hand side, but because it is on the top on the right-hand side, it must go to the bottom on the left-hand side. So it's going to move down. So now I have C over lambda equals nu. Nu, yes. Greek letter, nu. EW, yeah, no. Nu, nu, nu. Then when you go to solve this, if you have written it this way, you should rewrite it as nu is equal to C over lambda, because then you can show the plugging in a way that makes sense. You're writing your mathematical sentence from left to right. Yes? The number of waves? No, that would be just like, that would be a frequency. Yeah, it's just a number of waves. Yeah. Okay, so what we would do is we would solve it that way. And like I said, if you found this whole process of going from here to here to be a bit confusing, I got your back. Just let me know. I'll get you stuff. Okay? Because really, with my regular grade 11s, we did spend time going through this, and we haven't done that. So let me know if that's a thing you would like. So now we have C, which is 2.998 times 10 to the 8. And our unit is meters per second. I'm going to write it like this just to get you used to it, okay? And then we have that divided by 589 nanometers. The easiest way to do that is to just write 589 and then write times 10 to the negative 9 and replace the nano with times 10 to the negative 9 meters, because that way you don't have to do any like fancy converting nonsense. Yes? Just replace the nano with 10 to the negative 9. So, how are we with plugging that into our calculator? You're a bracket guy? If you need brackets, you need to call me over and let me show you how to use your calculator. Why on earth would you use brackets here? That's so many wasted keystrokes. No. Why would you need brackets? Just in case. Now, if you're having to do that, it means you're punching in you're using the wrong button on your calculator to type in times 10 to the 8 and times 10 to the negative 9. Are you using these buttons? Whoops. Or are you typing or you should be using one of these three buttons. They're all labeled differently on the calculators, and what they will do is they will automatically bracket that whole thing for you. So if you type in 2.998 EXP 8, it says that is all one number, you don't need to bracket it. Yes? You do not need to put brackets around that. Your calculator considers this to be just one number. And then you would, and then times 10 to the 8? Yeah, no. Yeah, no, it considers that all to be one number. Yes? Let me take a look because they're probably different. Now, let's take a look at what happens with our units here, because it is important that you see how the units work here. Meters cancel out. What are we left with? We're left with per second, and that's fine. That's what frequency is measured in. If you prefer to write it as hertz, you could write it as hertz, but the unit seconds to the -1 or just per second is fine. It's just like cycles per second. It's how many waves pass a point per second. Yes?
So per second would be waves per second.
Yeah, it's how many wavelengths pass a point per second, but it's not waves per second. Okay, because the wave is like the whole thing. It's how many wavelengths pass a point in a second. Not even wavelengths per second, just per second. Okay, yes. Yeah, let's take a look at, yep. So 5B and C, what? Oh, 5B might be wrong in the answer key, I don't know. I'm assuming if you think it's wrong, it probably is because, you know. Oh, if Jeremy Tom thinks it's wrong, then yeah, obviously it must be wrong. So 5B, in 5A, you have calculated the energy. What was the energy found to be in 5A? Okay. Okay. Now, that is the joules for one photon. Yes? One photon. We don't want the energy for one photon, we want the energy for that many photons. Okay? And apparently my answer key is wrong for this one, so, you know, bear with me here. So this is the joules per one photon. Okay? And so we now have not just one photon, we have 4.0 times 10 to the 17 photons times 3.11 times 10 to the -19 joules per photon. And so we get, let's find out what answer we should get, 4E17 times 3.11 E -19 equals 0.1244 joules, which would become 0.12 joules. Yes. Yes. No. No, but you have to write it so seldom it's not going to be a big deal. Like molecule, you have to write all the time. Photon might come up like maybe once on an AP exam, maybe, or maybe not. Do you know what I mean? Just write the whole thing. And quite frankly, MC for molecule is not standard. That's what I use. So sometimes people will do like molec or something like that, or you can like define it at the beginning of your question. Let MC stand for molecule. No, because different questions get marked by different groups. Yeah. However, you're probably not going to have to use that symbol in more than one question. So, you know what? If it's only once or twice you have to write it, you can just write molecule and be done with it. Yeah. Yeah. Would we like to look at C? Okay. So we are starting with 1.3 times 10 to the -2 joules. And we want to know how many photons. So wouldn't it be nice if we could cancel our joules and find photons? Yes, and guess what? We have that, right? We just have to flip it upside down. So there is 3.11 times 10 to the -19 joules per one photon. Okay, and so we do that and we get 1.3 e2 negative divided by 3.11 e negative 19 equals 4.18 times 10 to the 16 photons, but we would have to round that then to 4.2 times 10 to the 16 photons. Okay, yes, Matthew. Sorry? To be or not to be? Oh, alas, poor Yorick. I knew him well, Horatio. All right. So we have 103.4, which sounds like a radio station, megahertz, and this is our frequency, and frequency is represented by the letter nu, okay? 4. Yeah, yeah, it goes mu and then nu, so it's mu, nu. Anywho, so I would like this to be in SI units because all of our constants and everything are in SI units. And I know that you should know that 1 hertz is equal to 1 per second. Okay, 1 second to the negative 1. Now, chances of them giving you the value in hertz on the AP chemistry exam, I think, is quite low. I think they will actually give you the value in seconds to the negative 1 to start with. Okay? Now, what does the prefix mega mean? Times 10 to the 6. So we're going to write times 10 to the 6 seconds to the negative 1, and we have 103.4 times 10 to the 6, right? Because this takes the place of the mega. Yeah, and then hertz is seconds to the negative 1, so that's what we've got. We want to find the wavelength. Okay, and I'm going to look at my formula sheet, and I'm going to say, do I have something that relates frequency and wavelength? I do. I have C equals wavelength times frequency. So once again, I'm going to do some algebra here. I want this guy all by itself. So I'm going to move the nu from the top on the right to the bottom on the left, so it becomes C over nu is equal to lambda. And then we have lambda is equal to C over nu. I'm going to put it in a straightforward left to right sentence. 2.988 times 10 to the 8 meters per second, or second to the negative 1, over our frequency 103.4 times 10 to the 6 seconds to the negative 1. Now, do you see how this actually makes canceling those seconds to negative 1 pretty straightforward, right? So that's why I kind of like it this way. Did you have a question? No, you're good? Okay. So then we can just do our math on that. So we have 2.988 E8 divided by 103.4 E6 equals 8897, which would round to 2.0890, and my unit, all that's left is meters. Yes. Oh, what? Oh, thank you. 2.998, which probably means my answer is wrong too because I typed it in wrong. Okay, 2.998 E8 divided by 103.4 E6 equals 2.8994. There we go. 994. And so then that would become 2.899 meters. Okay, and that's quite a long wavelength. Radio waves have a long wavelength. Yeah? So from peak to peak. So if this was your, this would be 3 meters. Or from trough to trough, okay? So wavelength is from peak to peak or from trough to trough. Trough. You guys know what a trough is? It's the bottom, that little dip. Did that answer your question, Matthew? Okay, cool. Yes. Okay. It'll come to you. You can ask later. Okay. Yes. Yeah, put your answer in meters when meters make sense. If you had a number that was like something times 10 to the negative 9, you might want to put it in nanometers, right? Or even if it's like times 10 to the negative 7, you could probably like, or, you know, you can kind of make it nanometers if it makes sense, right? Yeah. Alrighty, are we feeling better? Yes, you have a question. Okay. Waves are the same, yeah. It's called a sine wave. Yeah. And so you do math with these when you're, like when it gets fancier, when it goes beyond my ability to do this, that's when the physics takes over. And yeah. Yeah. I assume so anyway. I don't know. I only took first year physics, so yeah. That was enough. I wish I had learned more physics, but I didn't. Okay, so how are we feeling about that? Good enough? Like I said, let me know if you would like the extra resources, okay, on just the algebra part. Yes. Yes. Yeah. 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 When you have those transitions down to n equals 1, those are all UV. Okay, any transition down to n equals 1 is UV. Doesn't matter, they're all UV. Yeah. Almost all the transitions down to n equals 2 are visible. I think there's like one that's not. It's like infrared or something. Yeah. Yes. Now, just to make sure that you feel good about it, this is actually quite a nice picture of the N equals of the Lyman series and the Balmer series. This is on, this was your reading from yesterday. This is on page 29. Yeah? Oh, maybe it wasn't. No, this is what I was going to have you read tonight. This is what, no, you're good. So I was actually, because I didn't want to give you too much to do, so this is actually going to be part of tonight's homework, is to read this part of it so that you get that review, plus you see some better pictures of things, okay? Okay. What have we got coming up next? Oh, this is extra practice. So we'll leave that for a little while. You can do it later once you've forgotten a little bit, right? Okay. So we did mass spectroscopy. How are we feeling about mass spectroscopy? Thumbs up, thumbs down, thumbs in the middle. I've got 5 people voting and 2 of them are sort of thumbs in the middle. Okay. So in essence, mass spectroscopy, you throw particles through a big machine and it puts magnets and the particles bend, okay, in response to the fact that there's magnets there, okay? So they go, whoa! Now, if you are a bigger, heavier particle, will you bend more or will you bend less than a little teeny tiny particle? You'll bend less, yes? So what'll happen is you'll fire these particles, like these isotopes of, say, chlorine or something, and they'll all get fired down, you know, a channel. The chlorines that are, and then there will be some bendy magnet things, like magnet here, and one of them will bend more, and one of them will bend less. And you'll have like a detector screen over here, and this will be like chlorine 35, and this will be chlorine 37. That did not get bent as much because it's got more momentum. It keeps going more in the same direction that it always was. You're going to get that detector, you're going to send a whole sample of your matter, so a whole bunch of different atoms, and every time you have a chlorine 35, it's going to bang into the screen and it's going to register on the machine. Okay? Every time you have a 37, it's going to bang into the detector here, okay, instead of here, and you'll get a registry on the machine. And then the machine will tell you, it will produce a spectrum that looks like that. Yes? So you'll be like, oh, I have more chlorine 35 than I do of chlorine 37. How do I know how much I have? I can read it off of the graph, right? So I can be like, how much 35 do I have? That's going to be about, well, 70 is here. Oh, have we lost something? What have we lost? An eraser. Was it a special eraser? Okay. Okay. So this is going to be, this is 70, so I'm guessing that's maybe 76%-ish. About 76%. Okay. Down here, we have, I don't know, here's 30. Oh my gosh, that looks to be about 24, doesn't it? La 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 la. About 24%. So the only thing that's different about this than the stuff you did over the summer is you probably have to read the graph to determine your percentages. Excuse me. So you would then say, do we remember how to calculate the average mass? You take your decimal percent and you multiply by the mass, and then you take your decimal percent of the other one and you multiply it by the mass, and then you add the two together. So in this case, you would have 0.76, that's your decimal percent of 35 AMU, plus 0.24 times 37 AMU, and that's going to give you your average atomic mass. And you'd be like, okay, I've got 0.76 times 35 plus 0.24 times 37, and you get 35.48, which is really close to the 35.5 that you get on the periodic table. The reason it's not exactly 35.5 is because I am estimating these things, these numbers, percentages from a graph, right? I don't know my exact number. And that's really all there is to it. Now, if you have something like this, and you're like, oh, I have an unknown element, I don't know, what is it? Well, it's got to be something whose atomic mass is close to 80, yes? So we're looking at, if I go to a periodic table, oh, Evan, are these yours? Yes. I was like, I put them somewhere safe because I'm like, I don't want them lying around, but then I'm like, oh my God, I almost forgot about them. So periodic table. Yeah. Something that's around 80. So we're looking at selenium, bromine. So here's my two candidates. Selenium, which is 79, and bromine, which is 80. Right? Those are the masses, essentially. Bromine's actually 79.9, but you know, close enough to 80. And I would look at that and I'd be like, well, I have a 50%, which is 80. And I have, let's see, 25% and 10% and 8%, which are below 79. So all together, that would be how much? 25, 35, 40, 3%. I'd be, if I were just ballparking, I'm not very good at math, but I might guess it's selenium, but I could be wrong. It could be bromine. I would actually want to chug the numbers on that one. So I would actually chug the numbers, and I'd be like 76 times 0.1 times 77 times 0.08. And then I would have 78 times 0.25. Is this making sense? Yeah, and then I would have 80 times, that's about 50. And I would have 82 times, that looks to be all 8 or 9%, something like that. It's going to be close, 0.0, we'll call it 0.08, maybe 0.09. It looks kind of between the 8 and the 10. You're going to get a number that's fairly close, right? 7.6, 0.08 times 77, 6.16, 78 times 0.25, 19.5, 80 times 0.5, 40, and 82 times 0.09. And you'll notice I'm not being very careful with my sig figs here. That's because I'm reading this data off a graph and I'm trying to get, like, you know, figure out the closest molar mass, okay? So I'm not too concerned about it. I add those all up. 7.6, 6.16, 19.5, 40, 7.38 plus 6.16 plus 19.5 plus 40 plus 7.38 equals, oh look, it's 80.42, which is a little bit too high, but it definitely means it's not selenium. It would have to be bromine. Okay, and that's probably just because my approximations weren't very good. Huh? The video said it was selenium? Oh. Okay. Okay, well, that's fine. I would go with the video's numbers because they're probably better than mine. Right? Yes. Well, if you do, you can just be like, they'll give you most of your credit, right? And quite frankly, most of your credit, a 9 out of 10, is better than 90% of the other people writing the exam. Yes? Not kidding you. An average score out of 10 is about 3 for like a given question. Yes? Yes? So, yeah. Well, this is the thing, it all gets scaled, which is why I'm trying to get you used to being scaled. Because if you walk into that AP exam and you come out feeling completely beaten up, you won't even know your mark until July. So I'm trying to get you used to that whole thing so that when it comes to that AP exam and you graduate and you know, and Ms. Fence going, no, it's okay, your grade gets scaled. No, you're fine, your grade gets scaled. You know, you could come out of that feeling like really awful for like a month before you even know, like 2 months before you even know what your grade is, right? Yes. Yeah. No worries. Oh, so there's percent abundance, which is like obviously a percent. And then the relative abundance is where it's done as like a decimal percent kind of thing. Yeah, pretty much. Yeah. Okay. Anything else in here that we wanted to take a look at? That one looks pretty straightforward. Yes. You would want to explain why, right? So you'd be like, well, I got 78. I am choosing selenium, or 78.9. The only element close to 78.9 is selenium, which has a mass of 79. Probably, yes. It will. If it says justify your answer, then it would be wrong to just say SE. Yeah. Yes. Yes. Right. I don't actually think this is going to happen, okay, because I don't think they want you doing that much math, okay? But you could do it, right? And you just have to figure out your percentages by saying, oh, this is 1, this is 0.466. Obviously, that can't be 100%, right? Because that wouldn't make any sense for me to have 2 isotopes and one of the isotopes is 100%. So one obviously can't be 100%. So you just add the 2 together to give you your total and find the percent by taking 1 divided by the 2 together. But I don't think that's going to come up. Okay? Yes. Yes. They are interchangeable. U and AMU are used interchangeably. It's fine. Yeah. Okay. Any other questions from here? We're good? Okay, very good. We did that. Oh, I wanted to go through just the last little bit of this because we had started talking last day about those standing waves. Do you remember our standing waves? Okay. Do we want to see the video again or are we good? We want to see it again? Okay. Okay. Let me grab it then. Because we didn't get a very good look at it last day. We were all packing up and stuff. So this is Unit 9, atoms and their electrons. Yes. Excuse me, I'm trying to listen to somebody. Yes. 9.3? No. Nope. That's not the one I wanted. Click the wrong one. Sorry. I want 9.3a. There we go. Grab that. Oh, and if you want to know how to say this man's name, Louis Dubreuil. He's French.
Bonjour, this is Julian the Frenchman who makes French pronunciation videos here on YouTube, and we are looking at how to pronounce.
Oh my God, this is killing me. Okay.
Then we are looking at how to pronounce the name of this French physicist and aristocrat who made groundbreaking contributions to quantum theory. How do you say his name? Louis, which is of course how we say this in French, silent S. Louis de Broglie. Louis de Broglie. I know it is an unusual pronunciation. It's got anything or hardly anything to do with how it is spelt, but that's how it is said in France. Louis de Broglie. Louis de Broglie, French physicist. Here are more videos on how to pronounce more names from science and quantum energy theory, the science in general.
Okay. He's not a random guy, he's important. Louis de Broglie was the one who came up with wave-particle duality. He was the wave-particle duality guy, okay? So important to know how to say his name. And if you come across Americans, they have no idea. They'll be like de Broglie, and it just pains me, yes. Because you look at it passing through a vacuum and that's how it behaves. It behaves like a wave. You can also look at, there are interference patterns when you shoot it through, like there's a double slit experiment.
It's connected to what's called a wave driver. It's
Okay,
just
hang
a
on.
speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps
Okay,
up,
so we're just going to pause this for a second. There are experiments that showed a wave-like nature. I have not gone into those because you are not required to know them, explain them, understand them, anything. If you are interested, you can read about the double slit experiment, and it's in it's in the Big Black Book. Yeah, the Big Black Book is actually really good. It does delve deeper into a lot of the things than I am spending time on here. Yeah? Yeah.
Up and down while he sends away.
Okay, so we're not going to watch the whole thing because we did watch part of it last day.
It's basically the scenario of a jump. Now, I can find any of the other, all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5 is 25.5. And there we go.
It was actually better before, I thought, but you know, whatever.
So that's the third harmonic. How many wavelengths is this? Well, it's 1 and a half. 1 and 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high-speed camera and verify for yourself that it is 1 and 1/2 wavelengths.
It would be nicer if we didn't have lag, but you know.
So again, third harmonic, 1.5 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic would be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
And we're not going to do that. Okay, so if you're interested in that, that's physics, and you're welcome to watch his next video. You have the link to this one in your book. Okay, but what, pardon me? That's as far as we go in this course, okay? But if you're interested in the physics of it and the wave physics stuff, definitely go check it out. It's interesting stuff. All right, now we're going back to here because here is another video with some very pretty representation of the blobby areas where electrons live, those probability fields. This is on page 46. Bingo. As we know at this point, blobby shapes.
Thanks to Google for sponsoring a portion of this video, for supporting small businesses, and for helping people find jobs. More about all that at the end. Atomic orbitals have long been a source of frustration for me. On the one hand, you have simple cartoon diagrams that make them feel friendly, but which are so varied and vague they don't really convey much beyond the basic idea that atoms have a nucleus and some electrons. Some people try to take the cartoon diagrams and make them feel more random or quantum, which is an improvement, but they're still very much just cartoon stand-ins for the vague idea of atom. On the other hand, you have atomic orbitals depicted as fuzzy clouds or balloons or rainbow donuts, which are definitely more technically accurate or technically inspired, but none of which feel like they give me a sense of what's actually going on. Like, what does this blobby thing have to do with orbiting electrons? Is the electron inside it, or on the surface? Why do some of them have blobs and others donuts? And why are some of the donuts rainbow-colored? I want to know what an atom looks like, and I want that picture to actually have something to do with the nitty-gritty reality of atoms, since they are indeed real things. You know, like how a diagram of the solar system is both a totally not-scale caricature, and yet also represents the very real idea that the planets all orbit the sun in roughly the same plane, and that some are farther out and some are closer in, and if it's animated, we get to see the closer planets complete their orbits more often. It's a nice picture, and that's what I want for atoms, a good picture. There are a few things I'd like that picture to get across, some of them because they're important to the physics of atoms, and some of them because they're questions my brain wants answers to. Like, where is the electron? How fast is it going? How much energy does it have? How big is this picture relative to other pictures? Of course, the wave-particle nature of quantum mechanics means some of these ideas, like the electron's position, don't translate exactly from our everyday intuition to the atomic scale. But there is a way of thinking about wave-particle duality where you picture the wave function as a bunch of water, and the particle as a speck of dust in that water. The particle is mostly guided by where the water goes, and the water is guided by the equations that determine how water behaves depending on its circumstances. And if you apply the mathematics of that idea to atomic orbitals, and then render it in 3 dimensions, here's what you get. Isn't it beautiful? Here's another. And another. And another. In fact, I made a bunch of these. And they're all mesmerizing and beautiful, and isn't the ground state of the hydrogen atoms just so cute? And aren't the excited states so majestic? There's so much structure and detail in them, I just love it. You can see patterns in the orbitals, and you can get a sense that they actually are orbitals. I mean, something is orbiting. Okay, so I do have to be clear. The dots don't each represent a separate electron. The whole collection represents the wave function of a single electron, and the individual dots represent all the places that electron could be. A higher density of dots means a higher probability of the electron being there. The bigger orbitals are the ones with higher energies, because electrons with more energy are more likely to be far away from the nucleus. The motion of the dots is showing the flow of the wave function, and does correspond to an extent with its actual angular momentum, though they're not electron trajectories. Unless you think Bohmian trajectories are real, in which case they really are electron trajectories. I'll let the philosophers of physics fight that one out. But the point is, these visuals are created by representing actual electron wave functions in a visual language that our brains can understand, that of objects and light and shadows and motion in 3D space. There's actually stuff orbiting, and they're pretty. I hope you like them as much as I do. Oh, one final thing. I 100% get these are not easy to draw. So if you want a cartoon representation of an atom that's simple but more closely based in atomic physics, here's my proposal. It's based on the orbitals from the p block of the periodic table. One of them has the electron orbiting one way, one in the opposite way, and in the third one the electron is orbiting the same amount, but around some perpendicular direction, and we can't know which is why the dots aren't moving in the middle orbital, and why I've drawn a dotted line and question mark for the sideways circle. And if you want, you can add an electron to each orbital, or two electrons.
At this point, he's just sort of getting off into a bunch of stuff. But yeah. So I'm going to let you do these exercises for homework, okay? If you're wanting a little bit more about this, actually might be a good opportunity to do a little reading in here, okay? Because really your homework is only that. It's like one page. So why don't we say that this would be a good day to do a little reading about 6.5? Let's see, 219. What is 6.5? I'll put the homework on Teams. Hi.
One of them is like, is it just like, help explain why
and I actually wanted to get to this today, but the class ran out of time. If you look at this, you have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7 wavelengths. Here you have 1, 2, 3, 4, 5, 6, 7, 8 wavelengths. 7.5 is not allowed because you'd end up with this little like gappy thing.
Wait, so does the first one always have 7?
No, it's just that this is a nice one to see. You can look at 2 wavelengths, but they're not very pretty. They don't look much like waves, do
The
they?
first one, so it'll increase as it goes up.
Yeah, so
And then
so 2 is going to be the smallest, and then there's going to be 3 wavelengths, and then 4 standing wavelengths.
Yeah.
Okay, and then we'll get to 5, and then 6, and
But
then
why
7.
can't
and
it
then
be
8.
like, well, yeah, what if it's like a different wave length? You know what I mean by that? Like,
Yeah, but no. Yeah. I.
like in the video,
Yeah.
like the dots,
Yeah.
like where is the dot? Like,
The electron is the blob. It's just a wave function. It's a probability field.
so it's just
That's where it could be. If you look at it, if you do an experiment to see where it is, it will collapse into a single point. And you'll be like, oh, a particle! I can deal with that. And that particle will be somewhere within that wave function. Within that probability. And honestly, you don't even need to understand it a little bit. You just have to be like, okay, sounds good to me. There's an electron in that blob somewhere. Yeah?
so like it can go
Anywhere in that blob, whether the blobs are dependent or not. Yeah. Okay? And at some point, just let it go. Be like, I'm not going to understand this, because you're not. And just be like, okay, the electron is in the blob somewhere. Yeah. I mean, electrons move, they kind of spin, they love atoms. Yeah. I don't understand that either. At some point. Fine. 6.5, but I'll put it up on Teams because I haven't 100% decided.
Is it like important?
Um,
Because I don't have the.
it's online.
Oh.
Yes.
So are the rings not?
The rings are not like what it is really in actuality at all. The rings are just like this imaginary fantasy world that we live in that makes it easy to visualize. Yeah. There's no rings. There's blobs.
So the blobs are where the electrons are.
Yeah. Yeah.
And then if there's like two, then any two could be anywhere in that.
Yeah. Anywhere in that blob.
What happens if it gets like now some elements have like 100.
Mm-hmm.
Same thing.
So there's many more blobs.